was better.
Okay, so just wait.
No, not this. No.
Yeah.
There are too many things. I mean, no. It's...
Now?
Yes,
yeah,
stay
now
where you are.
Yeah. Don't do anything. Yeah.
Yeah. So start the recording and start the lecture.
Yeah. I'm sorry for the trouble. Yeah. Welcome back to the APRG seminar this week. And we are very glad to have Jean-Philippe Anker on Allianz. And then he will talk about smooth barycentric decompositions of Weyl chambers. Yeah, Professor Anker.
Okay, thank you very much for the invitation and the giving me the opportunity to present you this some work I have done with my former PhD student Zhang. How much time do I have for the presentation?
1 hour.
You can take 1 hour.
Okay. So as I know that people in India know symmetric spaces quite well, it gives me also the opportunity to present in more detail something which I have never been able to present in other talks. So in the first slide is very sketchy. And it's I have just gathered on this page this general structure of Riemann symmetric spaces of a non-compact type. So these spaces are quotients of a semi-simple Lie group with some standard assumptions. You can think, for instance, to SL2R and quotient by a maximal compact subgroup. So for SL2R, the maximal compact subgroup is, for instance, SO2. And the quotient is then manifold with non-positive curvature. And for the example I mentioned, it's the classical hyperbolic plane. So for these spaces, there are there is one main decomposition, which is the Cartan decomposition, and it generalizes the classical polar decomposition in Riemannian manifolds. So in terms of the group G, this decomposition reads G is equal to K exponential of some cone, which is an open closed Weyl chamber called A plus and closure K. And so in the symmetric, if you make the quotient by K on the right, you get G equals K times G mod K is equal to time of K times exponential of this cone. So in rank 1, the exponential of A plus is just a half line, and these are the polar coordinates. And in higher rank, you have a decomposition but with a cone. And for instance, for SLNR, this cone is parametrized by the eigenvalue of positive definite symmetric matrices. So on this symmetric space, or on G, there is a Haar measure, and it writes a constant times the integral of the Haar measure of K, the integral of the Euclidean Lebesgue measure on A, and actually A plus in this cone, and times dk2, which is the Haar measure on K on the right. And there is a weight, and this weight is exponential. So there is an explicit formula. It's a product of hyperbolic sign, but the main feature is that the behavior is exponential. So it makes the analysis completely different from Euclidean settings or nilpotent case or so on. And there is an important vector inside the positive Weyl chamber, which is this rho. So I don't want to enter into the structure of symmetric spaces, but it's the half sum of the positive roots. It's roughly in the middle of this cone, and it governs, for instance, you can see the line above. It governs the growth of the Haar measure. And now there are 3 dimensions which are important in analysis on symmetric spaces. There is the rank, which I called L, and it's the dimension of this cone, in the dimension of A. There is a manifold dimension D, which is equal to L plus the sum of multiplicities, positive multiplicities. And there is a capital D, which is called pseudo dimension or dimension at infinity, and which is equal to the rank plus twice the number of positive reduced roots. So roots which have such that roots alpha, such that alpha over 2 is not a root. So I have gathered here essentially the mean notation. Do you want any more explanation, or is it fine?
So
That's fine.
why this is called? Okay, yeah, I will ask the question back then. Okay.
Sorry, yes?
No, this is fine. Okay.
Muna, the screen is very blurred. I don't know, it's only for me or for everyone.
No, for everyone. Yeah.
Blur.
I can't read any.
I
Just
think
wait.
it is
It will
something
take.
to do with Muna's office room connection, because I can see Thangavelu clearly, but not Muna.
Oh,
Correct.
yeah, it's becoming
Okay,
better.
yes.
Yeah.
Yes, it's
Yeah, it's
sharper
better.
now. Yes.
The screen
clear?
is
So can you move to the next page, please?
Yeah. So are
Yes.
you able to read it? Yeah.
Yeah.
So on this page, I have tried to summarize, I mean, the spherical Fourier analysis on symmetric spaces. So on symmetric spaces, there is a Fourier transform. I don't want to define it because it would involve too many technicalities. But this Fourier transform for bi-k invariant function on G, so for left k invariant functions on the symmetric space, it reduces to something which is much simpler. And this is called the spherical Fourier transform. And this spherical Fourier transform looks like the classical exponential, the Fourier transform on R, or like the Hankel transform on Rn. So it's the integral of the function f against. Oh, it's again not sharp.
No.
Okay, it gets better now. So it's
Yeah.
So it's the integral of f against a special function phi minus lambda x, and this function is called the spherical function. And so if you don't know the subject, you should think that this spherical function is an analog of, for instance, Bessel functions for the Hankel transform. And there is an inversion formula. The inversion formula involves the same function, phi lambda of x. It's like in the Euclidean case, you know, there is just a small change of sign. But the novelty now is the fact that the inversion formula involves density. It's called the Plancherel density, and this Plancherel density is given by the function c, the Harishchandra function c, of lambda to the power -2. And no, can you come back to the page before, please? Yes. And so this Plancherel density is fully understood. I mean, it's a complicated expression, but completely explicit in terms of gamma function. The main remaining difficulty in the subject is the fact that the spherical function phi lambda of x, although there are lots of information available, the behavior is not fully understood, especially if lambda and x go both to infinity. So this was a very short presentation of spherical Fourier analysis on symmetric spaces, and this is the analysis that I have used with my collaborators to analyze fundamental solution of PDEs. So can you switch to the next slide, please? Yes. And among the PDEs we have considered, there is the Schrödinger equation. So in some sense, the Schrödinger equation is the heat equation with imaginary time. And while the wave equation, I think everybody knows the wave equation, the difference is that you have two initial data instead of one. And most of the analysis of the study and of the result for the two equations are very similar. So I have decided in the next slides to talk mostly about the Schrödinger equation, because the statements and the proofs for the wave equation are usually more difficult and more involved. So can you switch, please, to the next slide? So now I turned. It's not sharp, at least on my screen.
It will take some time.
Very blur.
Okay.
Yeah, it will.
You may turn off your video.
Okay.
It will help.
So if you consider the.
Okay, just wait. I'm turning up my video.
About the screen also gone.
No, it's okay.
Yeah.
Okay. Yes. So now I consider the Schrödinger equation, and for the Schrödinger equation, there is a there are formal solutions. So first of all, if you look at the homogeneous equation, so when the second hand, which I call capital F, is equal to 0, then it's given by the Schrödinger propagator applied to the fundamental solutions, to the initial data F. And on symmetric spaces, it's given by a convolution with the Schrödinger kernel. And this Schrödinger kernel can be expressed by using the inverse spherical Fourier transform. So this is the formula, the second formula on the slide. And you see it's the inverse spherical Fourier transform, and the corresponding multiplier is simply e to the minus I rho square plus lambda square times t. And formally, it's the heat kernel, but where instead of having a t, one has it, so it's the heat kernel, but with imaginary time. And now if one wants to look at the inhomogeneous equation, so the equation where the right hand, there is a function capital F on the right hand side, then there is a well-known the well-known Duhamel formula, which tells you that the solution is given by the solution of the inhomogeneous equation plus an integral involving the right-hand side of the equation.
Not visible. Not visible.
And you see, so the whole problem consists in getting precise information on this Schrödinger propagator e to the it delta and on its kernel st. So in the next slides, I will give you here. I give first the estimates which have been obtained for this kernel. So just the pointwise estimates, and for the in rank 1 with Vittoria Pierfelice, we obtained 15 years ago an estimate which is I think sharp. And you see that in the Euclidean case, for instance, the Schrödinger kernel is just bounded by the value of t to the power minus the dimension over 2. Here there are two other ingredients. There is an exponential decay in space, which plays an important role, times some polynomial factor in also the distance to the origin, which is called r. But actually this factor is not very important for the rest of the analysis. The main factor is this exponential decay in r. And then one novelty on symmetric spaces is that the power of t is not uniform. It's not like in Euclidean space, always t to the minus the dimension over 2. It's minus dimension over 2 essentially when t is small, but when t gets large, then it's t to the dimension at infinity or pseudo dimension divided by 2. And in rank 1, the pseudo dimension or dimension at infinity is 3.
We can't see
then,
anything.
Yes, so yes.
We can't see anything. Sometimes it's becoming very blur. Mona can switch off your video.
Yeah, I'm doing that. Just wait.
Maybe someone else can present. It's very blurred.
Maybe I can send it to Thangavelu, sir.
Yeah, just send it to me. We see.
Yeah, I have sent it.
Yeah, it hasn't reached. Yeah, it has come. Let me see. Yeah, there is some problem. Let me try to share my screen. No, it's going on. Where is my screen?
Just we are able to see your screen. Just open the PDF file.
Yeah, but it's already opened.
Anyway, yeah, you can see now.
Yeah,
It
let
was
me.
there.
Can you see now?
Yes,
Yes.
yes. It's
Yeah,
very
okay.
clear.
Let me.
Yeah, much better now.
This is the place. Yeah.
So it's, yes, it was this screen. Yes, so it's very sharp now.
Sharp estimate.
Yes, and so you see that in higher rank, then much later with Stefano Meda, Vittoria Pierfelice, Maria Vallarino, and Zhang, we obtained a similar estimate for general symmetric spaces. You see the difference. So the exponential decay in space is the same. Except that since now it's multidimensional, one has an inner product exponential minus rho x plus. The time decay is also similar. You have t to the minus the dimension over t for small t, and t to the minus the dimension at infinity over 2 if t is large. There's just the result is not sharp for the polynomial part, but fortunately it plays no role in the forthcoming analysis. So you see the main terms are the terms in red in these estimates.
So capital D is the pseudo dimension here.
Sorry,
The capital D is a pseudo dimension here. Notation.
Capital D is the pseudo dimension, and small case d is a manifold dimension.
Okay, thank you.
So can you switch, please, to the next slide?
Yeah.
Yes. So in the analysis of dispersive PDEs, of linear PDEs, there are two main inequalities which need to be shown in order to then to analyze nonlinear PDEs. I will not talk about nonlinear PDEs, but these two important inequalities are: the first one is so-called dispersive inequality, and this dispersive inequality it tells you what is norm, operator norm from LQ prime to LQ. So Q is between 2 and infinity, and Q prime is the dual index of the Schrödinger propagator. And so for small t, the result is similar to the Euclidean case. But for large t, the result is completely different. You see, it's t to the minus the pseudo dimension over 2. And you may notice that this estimate doesn't depend on Q. So it's a special feature. It's really a new phenomenon which occurs for symmetric spaces, and which in negative curvature, and which doesn't occur in Euclidean space. And then the second inequality, which is deduced from the dispersive inequality, it's called the Strichartz inequality, and it's an a priori inequality for solutions to the Schrödinger equation. So for in order to state this Strichartz inequality, one needs to introduce mixed norms. So these mixed norms, if you have a solution to the Schrödinger equation, U, it depends on the time t on the space x. So you first compute the LQ norm in x, and then the LP norm in t. And the Strichartz inequality tells you that the mixed norm, Strichartz mixed norm of the solution is bounded by the L2 norm of the initial data plus the P prime Q prime mixed norm of the right hand side of the inhomogeneous equation. And you may notice that on the left I have written P tilde Q tilde in the norm, on the right P prime Q prime. So P prime Q prime as usual are just the dual indices to P and Q, and PQ is a so-called admissible couple, and P tilde Q tilde is another admissible couple. And what is striking is that, but this was already known in Euclidean space, is that there are no connection between PQ and P tilde Q tilde. You can choose them freely. So please, can you move to the next slide? So here I have drawn the picture of the set of admissible pairs. So you see the P and Q is called admissible if 1 over P, 1 over Q belongs to the triangle in red, except the upper line. And the lower line, which is given by the equation 1 over P equals D over 2 times 1 over 2 minus 1 over Q. This lower line is the set of admissible pairs, but in the Euclidean case. So it means that for symmetric space, you gain all the triangle above the Euclidean line. You don't get better because if you look at the polygon below this line, actually this polygon is forbidden because of local problems. It's the local analysis which forbids the lower part. And
can you please repeat this, what you said?
Excuse me?
Can you please repeat what you said? That
No, I said I said that the global analysis, the large scale analysis, is responsible for the fact that you gain a triangle instead of just a line. But local analysis is an obstruction to gain anything below this line.
so for Euclidean space, you get below this line or what?
No. So, for instance, we looked also at homogeneous trees, which are discrete analogs of hyperbolic planes, and for trees, you have no local analysis. Local analysis is trivial. And then you get also all the polygon below the line. But on symmetric spaces, you have local phenomenon, local obstruction, which tells you that the Strichartz inequality cannot hold if you are below this Euclidean line. Did I understand? Did I answer the question?
Yes.
Okay, so now I have just listed what are the main tools which we have used. So the first tool is what we called smooth barycentric decomposition of Weyl chambers, which is really the tool which allowed us to obtain kernel estimates in higher rank. And it involves, I mean, some structure of symmetric spaces. So since I know that most of the audience knows symmetric spaces, I will devote the next slides to explain what is this smooth barycentric decomposition. And the other tools are, we needed to use the Hadamard parametrics for the wave equation. So for the wave operator, cosine of, so the fundamental solution to the wave equation, cosine of t square root of minus the Laplacian, or the other one, sinus of t square root of the Laplacian divided by square root of minus the Laplacian. And for symmetric spaces, one can slightly improve the classical Hadamard parametrics, especially for at infinity. One needs to get a decay on the solution for when the space variable goes to infinity. And then we use also a consistine, the consistine phenomenon, actually not the classical consistine phenomenon, but a version which I stated below. And this is the following version. If you have a decay invariant function, let's say measurable, or C infinity with compact support, if you want to be sure that everything works fine, and if you want to estimate the operator norm from LQ prime to LQ of the right convolution with respect to this kernel, then this is bounded by an integral involving the spherical function of index 0, and everything is measured in the space L of Q over 2.
Can I ask a question, Professor Anker?
Excuse me?
Yeah, can I ask a question?
Yes, yes, yes.
In this case, if the by-k invariant function k is non-negative, is this the norm of the operator?
I think so. Yes, because in this case you have the, I mean, this version of the consistine phenomenon is very close to some old work of Hertz, and there is a majorization principle which tells you in this case that you can reverse inequality.
Okay, thank you.
So I'm not fully sure that for a positive one it's exactly the same, but I think I would say so, but I don't bet it. I should think longer to make sure.
Okay, fine. Thank you.
But then in this case, I would try with the majorization principle to show the converse.
Okay. Thank you.
And but here the kernel we are dealing with are oscillatory kernels, so we just need the inequality.
Yes, of course.
And the last, so this consistine phenomenon is used to get the dispersive inequality for T large. And then, of course, in order to get the Strichartz inequality, there is now a standard machinery which was developed by Ginibre, Velo, Kiltao, and probably I should have mentioned before Kato. So we just apply these standard tools. So what I would say our main contribution is really the first tool, the smooth barycentric decomposition of Weyl chambers, which I'm going to explain. So I have started with a slide where I tried to motivate this tool, and it comes from the fact that all the fundamental solution, either for the Schrödinger equation or for the wave equation, are the fundamental solution. Their kernel are oscillating integral, which are given by the inverse spherical Fourier transform. And I have written here the expression for the Schrödinger kernel, and you see that you have this Plancherel density C of lambda to the -2. You have this spherical function phi lambda x, which is like I would say an exponential or a Bessel function, but it is essentially oscillating. And then you have another oscillating factor. So in order to analyze such oscillating integrals, one needs to do some clever stationary phase analysis, and you know that the main terms comes from the behavior around the stationary points, and then outside the stationary points, what you do essentially is integration by parts in order to get a better decay of the multiplier. So this works fine in rank 1. And in rank 1, you have explicit expression for the spherical function, for the C function. So everything is more or less explicit. And then you can really do this stationary phase analysis to get precise estimates of the Schrödinger kernel. And this is what I did with Vittoria Pierfelice, and for the wave equation with also in addition with Maria Vallarino. But in higher rank, there is a problem, and one of the main problem is that the Plancherel density, I wrote it here, it's a product of rank 1 expressions. So all these rank 1 expressions are differential symbols. So I refer to the classical notion in pseudo-differential for pseudo-differential operator. So it means that the function has a certain behavior at infinity, and then each time you differentiate it, you gain an additional decay. But so this Plancherel density in higher rank is, in some case, it's a differentiable symbol. For instance, when the C function is a polynomial. But in most cases, it's not a differentiable symbol. And so if you differentiate arbitrarily this density, you get no global decay at infinity. You get decay in some directions, but no decay in other directions. And so this was one of the problems. It was well known among specialists to overcome the difficulty of estimating inverse spherical Fourier transform in higher rank. And we overcome this problem by dividing each Weyl chamber into subsectors, and in each of these subsectors there is a specific direction, and if we differentiate along this specific direction, then we get a decay as if the Plancherel density were a differentiable symbol. So I will now explain what is this subdivision of Weyl chambers. So I wrote first a rough barycentric decomposition, meaning that I take a characteristic function of subsets, and on the whole Cartan subspace A, almost everywhere I get sets W applied to a sector Sj, such that the sum of characteristic functions is almost, I wrote, is equal to 1 almost everywhere, because there is all, I mean, the interior of these sectors are disjoint, but of course on the boundary you may add up values. So in order to construct this subdivision, I consider the simple roots, alpha 1 up to alpha L, and I consider the dual bases, which are called lambda 1 up to lambda L. L is the rank, so the dimension of A. And so the dual bases of the simple roots, it's known that they are this lambda 1 lambda L, they generate the positive Weyl chamber. Now I choose the subtector as follows. I call Sj the vectors in the positive Weyl chamber where the inner product with alpha j, so j is fixed, is maximal among all alpha k, among all projection on the other simple roots. And so the positive Weyl chamber is a union of the set Sj. And now if I take the action of the Weyl group W, then I get a covering of all the Cartan subspace. And in the next slide, I have two pictures. So please, could you move? I have two pictures of these sub cones. First, on the left, it's for A2, and on the right for the root system A3. So you see for A2, you have two simple roots, alpha 1, alpha 2, and you have A plus, it's a positive Weyl chamber. Lambda 1 and lambda 2 are the generators of this positive Weyl chamber. And I just split in two this positive Weyl chamber, and S1 is half of the positive Weyl chamber, which is closest to lambda 1, and lambda 2 is the one which is closest to lambda 2. And the same is the same for all root systems. So on the right, I have tried to make a picture for A3. So there you have lambda 1, lambda 2 in blue, and lambda 3 in green. And if I take now a slice of the Weyl chamber, I have, you see in red, you have the part of the positive Weyl chamber which is closest to lambda 1. In blue, the part which is closest to lambda 2, and in lambda 3, the part which is closest to lambda 3. And the dot in the center is the barycenter of this of the triangle. So you see, it's really a barycentric decomposition of Weyl chambers. Are there questions about this decomposition? So if not, now I move to the smooth barycentric decomposition. So the idea is, instead of having characteristic functions of this sectors W dot Sj, I take smooth versions, so functions which are smooth but look like characteristic functions. So it's a bit technical to define them, but it's not very hard. So this chi W dot Sj, they are homogeneous symbols, so it means that they are constant along half lines, half rays coming from the origin and going to infinity. It's a smooth, except at the origin, of course, and it's of order 0. And the sum of this chi WSJ is equal to 1, except at the origin. So it's a partition of unity, a smooth partition of unity. And there is an important property, a dichotomy, which is valid for these subsets. And this partition is the fact that if you fix a root alpha, an element W in the Weyl group, and a J between 1 and L, then you have either the root alpha is orthogonal to W applied to lambda J, or alpha applied to lambda is comparable to the norm of lambda for every lambda in the support of this chi of WSJ. So it means that if you differentiate now, if you want to differentiate, then when you get alpha W lambda J, sorry, there is a mistake. I should have written in the second line, or alpha inner product with W. No, sorry, it's fine, because lambda is in support of chi WSJ. No, it's fine. And so the application is the following. It means that away from the origin, actually, if you look at the Plancherel density multiplied by this partition of unity, then this behaves like a symbol of order n minus L. N minus L comes from the Plancherel density. Of course, this is away from the origin because the analysis at the origin must be dealt with differently. And if you differentiate along the specific direction W lambda J, then it behaves like a symbol, which means that if you differentiate capital N times along this direction the function, then it's bounded by lambda, this should be a norm of lambda to the power n minus L minus capital N, so the number of times you differentiate. And thanks to this decomposition, then one can use integration by parts and phase space analysis as in rank 1, because if you differentiate each time the density, so this was the boring term, the density, but in a subsector, then you get you gain decay at infinity. Okay, so this is the end of my talk, and I thank you for your attention.
Yeah, thank you very much for a very interesting talk. Now let's see if there are some questions.
I think I have some questions. So for the rank 1 case, what is the advantage you get? So you can share the slide, sir. Maybe.
Excuse me, the sound was bad. I didn't understand.
So in rank 1 case, what is the advantage in rank 1 situation?
Yes, in rank 1 situation, what is?
So you said that that rank 1's case, this whatever you are proving, that is easy to really handle, right? So how that
Yes.
is easy?
Yes. Could you come back to the statements in red?
Slide.
This one.
No. Much before the kernel estimates. Yes. No, before.
Yeah.
Yes, here. So you see, in rank 1, first of all, we started with the rank 1 because we had absolutely no idea at the beginning of what would be the behavior. And so we got this estimate. The estimate in rank 1, I think they are optimal. I have not proved the fact that it's the left-hand side is larger or equal to the right-hand side. I know that in some direction, the left-hand side behaves like the right-hand side. But
you mean say that you mean to say that two-sided estimate is there in rank 1? This what you have written.
Yes. This was proved. I proved this with Vittoria Pierfelice for hyperbolic spaces, and then with Maria Vallarino, we extended the result to Damek-Ricci spaces.
And the explicit expression of STR is there also in rank 1?
Sorry, the explicit.
So I am saying the explicit expression of STR is also known probably. Rank 1?
Yes. And yes, in this paper you have full details about the proof of the estimates. And in the second paper with Maria Vallarino, we give some regions where we know that the left-hand side is larger or equal to the right-hand side. But we didn't prove that. I mean, it's really comparable. But I guess that this is the. On the other hand, in higher rank, you see there is this small n.
Mm-hmm.
And this small n, we have some information in the paper with Hongwei Zhang and with the four authors, and also in the paper about the wave equation with Hongwei Zhang, we gave some cases where we have estimates of n, but they are not optimal.
But means I just want to know, n depends upon what kind of factors? And,
no, we don't know exactly. We didn't care too much because you see, since we for large T we applied the Kunzestein phenomenon. In the Kunzestein phenomenon, the exponential kills all the polynomial factors. So the exact value of the small n was not important for the dispersive inequality.
mm-hmm. And for the dispersive inequality for t greater than 1.
Sorry.
For
yes.
dispersive inequality, if you can you go back, sir? Can you slide? Okay, go to the next slide probably. Disperse. So for this, if mod t greater than 1, this operator norm doesn't depend upon q, right?
Yes. I mean, this is what we were surprised when we found this in rank 1, that it comes from the Kunzestein phenomenon. You see, because in the consistent phenomenon, you see that if you look at if you have a factor like t to the minus d in front of the kernel, it comes out of the integral, and it doesn't depend on q.
And the constant, what about does that depend upon Q?
Sorry,
So there is a constant, right? So that constant, does it depend upon Q?
which constant you mean?
No, this, so this for mod t greater than equal to 1, that operator norm is less than equal to some constant into t to the power minus d by 2, right? Mod t to the power d minus d by 2.
You mean if this t to the minus d over 2 is optimal or not?
No. He's asking in this inequality, this will be less than or equal to some constant times mod t power minus d by 2, whether he wants to know whether that C depends on Q or not.
Yes, of course, it depends on Q.
I think it will depend. Okay.
Yes, no, it depends. The constant depends on Q. It's just the power of T which doesn't depend on Q.
I just have another question. Can I ask?
Yeah.
Yes.
I mean, it's kind of vague, but the way I'm trying to say it, suppose T is small, then the norm of the operator does depend on Q. So is it analogous to Euclidean spaces when T is small?
You mean, for instance, the dispersive inequality?
Yes.
Yes, because I mean the general philosophy is that locally a symmetric space looks like a Euclidean space.
Yes.
And so one expects that that the phenomenon is similar and that the behavior should be similar to the Euclidean case.
Yes. Thank you.
Yes, and actually, this is always what I have in mind. So when I'm making computation, I for small scale analysis, I try to compare and to get the same result as for Euclidean space. And then for the large scale analysis, this is really where I think the negative curvature comes into play.
Yes.
May I ask something?
Yeah.
First of all, thank you, Professor, for this wonderful talk. In the rank, I haven't read your paper on this dispersive inequality on symmetric space, any of that, but I have read this multiply theory paper on Stanton Thomas, where they, I think, in a rank 1 case, they use similar decomposition, like they first decompose the integration of lambda from I from 0 and near the 0. And for I from 0, they use the horizontal series decomposition of the spherical functions.
Yes.
Right. And my question is that in the higher rank case, so there will be an component of spherical function on this inversion formula, right?
Yes.
But in the rank 1 case, we have this sharp like derivative estimates of the components of horizontal series decomposition of spherical function in rank 1 case, which we don't know in the higher rank case. My question is, how do you handle that component of spherical function of horizontal series decomposition?
If I understand, so what you say is that the Harishchandra, the converging expansion of Harishchandra in rank 1, it works for large space variables, yes. But in higher rank, it doesn't work if you get close to the Weyl chain, to the walls.
Yes, sir. Perhaps could you move to the last page, second last page?
This one?
Yeah, here. Yeah. Here in the derivative condition, I'm asking that since we're taking derivative del n w del lambda j,
yes.
chi lambda there will be also required some derivative with respect to lambda j of some component of spherical function, right?
Yes, but then we don't use the Harishchandra expansion.
Okay, and how do you handle that then?
Fortunately, it's enough to use the Harishchandra integral formula. You know that the spherical function is an integral over k.
Okay, that will suffice here. Oh, okay.
Yes, and then you get a phase which involves the imaginary exponential coming from the integral formula, and also the exponential factor coming from the multiplier.
Okay. So I will end this with my last question is that, so this kind of technique, I believe we cannot do that for Harmon-Miller multiplier, right? Because there we use usually. Like if I want to use this technique for a multiplier theorem, like Harmon-Miller multiplier theorem, you cannot use this technique in that kind of problem, right?
No. I mean, we developed this. It was specifically for, oscillating for kernels, for integrals which are highly oscillating multipliers.
Okay.
And I don't. I mean, one had really to divide. We don't apply this all over the space. We have to make several splittings, and then this is this was the main point where essentially by using classical tools we were not able to solve the problem.
Okay.
So I insisted in my talk on this aspect, because I think that it's something which may be helpful for other computation on symmetric spaces.
Okay. Thank you.
Abhishek, do you have a question?
Are there any more questions?
I can ask one more question.
Sorry?
Yeah, ask her. Yeah, are you going to ask Abhishek?
No, you can go ahead. Please go ahead.
So can I ask a question?
Yeah. Hello, Professor Anker.
Yes.
Yeah. So this thing capital D, why you call this as a dimension at infinity or pseudo dimension? What is the reason that people call that?
I mean, some people call it dimension at infinity or pseudo dimension. It's because I mean it's something which puzzled people. I think, for instance, in the I would say 90s, beginning of 2000, probabilists were puzzled by the fact that if you look at for instance, heat kernel, then you know that if you get rid of the Gaussian factor, the power of t which comes out for small t, it's t to the minus the dimension over 2, like in the Euclidean case. Mm-hmm. But if you look at large t, then it's strange. For all hyperbolic spaces, it's always minus 3 over 2. And so people were puzzled by the fact that it doesn't depend on the dimension. Mm-hmm. And so there were lots of papers by probabilists to try to understand from various point of views the fact that you get these 3 and not the dimension. And it's really related to some explanation was the fact that at infinity, symmetric space looks like the symmetric space with the same root system but multiplicity 2. So in some sense, the roots is the symmetric space with a group of isometry which is complex. So for instance, if you start with SL2R, then at infinity, the symmetric space or the behavior, for instance, of the heat kernel and other objects looks very close to the case of SL3C divided by SU2, and not SL2R divided by SO2. So this is why they call this the dimension at infinity.
Means if I understand correctly, if you look at this expression of heat kernel, if you look at for t greater than 1, so to the power minus q by 2 will come, right? Or sorry, t to the power minus d by 2 will come, right? Is that the reason? Or not?
I'm not sure. So if you look at in rank 1 at hyperbolic spaces, the power of t which you get for the heat kernel is t to the minus the dimension over 2 for small t, and t over t to the power minus 3/2 for large t. And this is the 3 here doesn't depend on the dimension of the hyperbolic space. And what I said is that people try to understand why you get this number 3 and not the dimension. And one explanation was that it was linked with what they call the intrinsic Brownian motion of the Weyl chamber, which is associated to the symmetric space, to symmetric spaces with complex group of isometries. So it means that in rank 1, it seems that the heat kernel at infinity behaves, at least the power of t behaves like the case of SL2C divided by SU2. And this is a strange phenomenon. I mean, for me, there is another explanation. The explanation for me is simply the fact that it's linked with the density, the behavior of the density of the Plancherel measure at the origin.
Oh, yeah.
If you look at the C function, at C density, it's C of lambda to the power minus 2, then at the origin, this expression behaves like the product of indivisible roots of alpha lambda to the power 2 square. So essentially it behaves like, let's say, the norm of lambda to the power twice the number of indivisible positive roots, which is exactly the factor entering the definition of capital D.
Okay, yeah. Yes.
Okay, so just one more question. So, Professor Anker, are you basically saying that, for example, in the rank 1 case, mod c lambda power minus 2 for small lambda is like lambda square, right?
Sorry, I didn't understand. Could you repeat, please?
I'm simply saying that whatever you were saying in the rank 1 case, it would mean that mod c lambda power minus 2 for small lambda is like lambda square.
Yes.
It doesn't depend on the dimension.
No.
So that's what are you trying to say, that the behavior of t as t goes to infinity in the estimate of heat kernel doesn't depend on the dimension is linked to this?
I mean, for me, it's the analytic reason.
Yes. Okay.
You see, because you always get this 3 in the rank 1. Always get this 3. It's not only for the heat kernel. It's also for the Schrödinger kernel. Also for the wave kernel. You have always something which is linked with the behavior at the origin of the Plancherel density.
Right, because estimate of the Plancherel density tells us that for large lambda, we have lambda power dimension -1. But for small lambda, it's always like R3.
Yes, exactly.
Lambda.
Yes.
Yeah, that's what you mean. Okay.
Yes, yes, yes. I mean, for an analyst like me, this is the meaning of these three.
Yeah, that's a vice for us. Thank you.
Utsav has a question, I think.
Yes, sir. So in your paper on dispersive estimates on the wave equation on Dirac-Ricci spaces, you considered a variation of the Hershey series expansion for large distance away from the identity of the group. So you had a modified version where the gamma coefficients also had decay in the spectral parameter. So do you have any analog of that for arbitrary rank?
I'm sorry, I didn't understand the question.
Okay,
I mean,
so
the sound was not good. Yes.
Okay, so is it better now?
Yes, it's better. Yes.
Well, thank you. So in your paper on dispersive estimates on wave equation on Dirac-Ricci spaces, you considered the away from the identity of the group, you had a variation of the Hershey series expansion for phi lambda, right? You had a which in fact had a lambda decay in the gamma coefficients. So I just want to ask whether you have a higher rank generalization of that or not.
No. I don't know any. I mean, it was a bit of a surprise, but because when we made the analysis in rank 1, I mean, if there would not, you mean you refer to the behavior at infinity of the coefficient capital gamma in the Hershey expansion.
Your modified series of Hershey series expansion, if I understand correctly.
Yes. So at some point, we realized that it would be helpful if this function decay better than what you expect from the formula, but in higher rank we didn't pursue in this direction because I think another participant asked already the question about the behavior along walls, because this Hershey expansion doesn't converge along walls, so you have additional problems there.
Yeah, of course.
Yes. So I don't know if anything about I mean better estimates than those obtained by I think it was Ganguly who obtained the estimates. Yes.
So in principle, like these barycentric decompositions you are doing here, is it like somehow heuristically speaking replaces that phi lambda decay you had in the rank 1 case?
No, it's not that simple. No, because we used we were very much also inspired by there were attempts in the past of Michael Cowling, Stefano Meda and Saverio Giulini to study the wave equation. What did they look? They look at the heat equation, the Poisson kernel, and the wave equation on symmetric spaces. And we use some of their ideas to express also some kernels by using the Hadamard parametrics. And but they just use the old estimates obtained by Bérard, and actually we realized that one needs to slightly improve these estimates. So this is contained in my paper with Zhang on the wave equation.
Okay, thank you.
And then we had to. It was really so when Zhang started his PhD with me, I proposed him. I said it's hard because with Stefano Meda, Vittoria Pierfelice, and Maria Vallarino, we had tried to estimate the Schrödinger equation and the Schrödinger kernel in higher rank, but we failed. Actually, what was quite strange, we got a rather good estimate for large time, but a bad for small time. And we were really stuck, so I proposed to Zhang to work again on this problem. And after one year, we still failed. So we switched to the wave equation, but for the wave equation, by mixing with this Hadamard parametrics, we were able finally, and using also this subdivision, we were able to solve the problem. And so later on, we came back to the Schrödinger equation and solved also this case.
Okay. Thank you.
Are there some more questions?
Can I ask a few questions? So my questions are mostly with the wave equation, though you have spent most on the Schrödinger equation. So first question is do you really know that the loss of regularity for the wave equation, the fixed time estimates for the wave equation on rank 1 spaces?
You mean for fixed time?
Yes.
But I think that for, maybe I am wrong, but I think that for fixed time, Cowling and his collaborator obtain already almost optimal results, no?
Okay, on the rank 1 space also.
No, in general. There was a paper in Annales de l'Institut Fourier.
Okay. I was not aware of that. Okay.
And I think for fixed time, but the problem was that they had no good control over the time. So I mean, our problem was really to get at least for the kernel good control both in time and space.
Yes. And
I think as long as the time is fixed, the estimates of Cowling, Meda, and Giulini, it's from 2000, maybe 4, something like this. In Annales de l'Institut Fourier, I think their results are sharp.
Okay, thanks. And also, people have studied this local smoothing kind of phenomena on these rank 1 spaces for the wave equation or for the local smoothing phenomena.
The smoothing effect. Yes, this has been studied by Zhang. After his PhD, he went to Ghent, and he worked with I think Vivesh Kumar, who I think was a speaker last week, and with Mikhail Rozhansky. And they wrote 2 papers about smoothing effects for symmetric spaces.
I see. Okay.
You can find the papers on archive.
Yes, sure. And also, one more kind of a philosophical question. with these improved estimates, can one expect to obtain estimates for the spherical maximal function and things like that on higher rank spaces?
For which operator?
I'm saying for the using the improved estimate for the wave propagator, can one
Yes.
prove results for the spherical maximal function on higher rank spaces?
I don't think, I'm not aware of any. Yes, there is one of your colleague in India, Bowick. I think he's considering this problem.
Okay.
I think before him, I don't know of any sharp or any deep study of the spherical maximal function.
Okay. Thank you very much.
Yeah.
So, Professor Anker, we want to upload your lecture in the YouTube, and if you, in case you allow us, so will it be okay?
Sorry, I didn't understand.
So what I'm saying that we have recorded your lecture, so can we upload it on YouTube in our official channel?
Yes. If you want, what I realized I didn't put any bibliography at the end. So if you want, I can add some bibliography and send you the updated version.
Yeah, certainly. Okay.
It will be good.
So slides and
Yes, for the slides. Yes.
Yeah. Okay. Thank you for agreeing to give a talk here.
No, thank you for. I mean, as I said, I had never the opportunity to present this decomposition because I had never an audience of experts in analysis on symmetric spaces.
So if you are asking about Swagat Eskere, and he's in the audience, so you can interact with him.
Yeah, I'm here. We met a long time ago.
Yes, of course, several times. Yes.
Can you turn on your video so that will be nice.
Sure.
And Professor Anker, you can also turn on your video.